Hi everyone. So today I'm going to present a great way to compare pixels. It is based on co-occurrence statistics. Now, Rotat is the lead researcher for this work. My name is Roy, and Shai is our advisor. Some of you may experience flashbacks from last year's Vision Day, where we presented the co-occurrence filter. Everything is okay. It does relate to co-occurrence filter. Let's start. So I'll start by motivating our problem with template matching. In template matching, we have two images. The image the template is taken from and the query image. And what we want to do is to find the template within the query image. So we translate it all over the query image. Now the big question is, what is a good similarity measure to compare the template to patches from the query image? So is it SSD? Clearly not. The blue colors here represent bad matches. The yellow and reddish shades represent good matches. Now, I said before that SSD is clearly not a good measure because first, it detects the wrong place. So SSD reports the top right corner of this image as the best match. And second, you can see a lot of yellow and red colors here, which indicates good matches, even for places that clearly has nothing to do with the template. So why did SSD fail? I plotted here the template and the ground truth, and I'm overlaying them one on top of the other. Now remember, SSD relies on color differences. Now you see there's no way to overlay the template and the query, ground truth, such that the sum of square differences will be low. Okay? Here's an example of a good heat map. It's a co-occurrence. And the goal of this presentation is to show you how to get this heat map. And I'll start by explaining what co-occurrences are all about, and that is best explained with an example. So we have an input image and its corresponding co-occurrence matrix. What we do is we pick a pixel and choose one of its neighbors, and then we vote in the co-occurrence matrix in entries according to those pixels' values. So we have a black pixel circled green and a gray pixel circled blue. So in the co-occurrence matrix, we go to the entries of black circled green and gray circled blue, and vote +1. But we don't do it just for one neighbor. We do that for all of its neighbors. So here's another example. And we do that for all pixels in the image. So here's another example and another example. Once we do it to the entire image, to each and every pixel in the image, we get the following co-occurrence matrix. Now, I color-coded the input image, so it will make it easier for us to understand what's going on here. Let's start with the green region. So you see the green region is made of dark pixels, which means the dark pixels tend to co-occur a lot one next to the other. And this is reflected in the co-occurrence matrix here, where we see that dark shades tend to appear a lot together. If we look at the yellow stripe on the other end, so the yellow stripe is the edge between dark and light. And you can see that the yellow stripe, it's very small, which means that there's a low probability for dark and light to co-occur one next to the other in this image. And it's reflected in the co-occurrence matrix. You see, we have dark pixels with bright pixels, and we get a low score for them. Finally, let's look at the red areas. Those are the checkerboards. Now, the checkerboards are patterns of black and white. Black meaning intensity level 0, and white 255. If we go to the metric, to this co-occurrence matrix in 0 to 55, that's what I zoomed in here, we see a delta, which means that black and white in this image tend to co-occur a lot one by the other. So that's the intuitive explanation of what's the co-occurrence matrix. Mathematically, this is how we compute it. So you see the brackets here, they represent indicator functions, which means that a pixel votes only for entries that corresponds to its value. Next, it doesn't make sense that pixels that are far apart will contribute as much as close neighbors. So we have this Gaussian kernel, which is inverse proportional to the distance in the image plane between two pixels. So if we take the contribution of this black circled green and the gray circled blue, they contribute a lot more than, let's say, the two green pixels, just because they're closer in the image domain. Okay, let's try and take this equation and use it for the tiger image. Now, the tiger image is an RGB image. Oops, so for RGB image, the range is very big. It's 256 cube, which makes the co-occurrence matrix huge. And the normal image is just not big enough to populate this matrix with reliable statistics. So what we did instead was to quantize the image. Here you can see the image. Here you can see the image of cluster centers, and for clarity, the cluster indices. Now what I want to explain is that here the co-occurrence matrix is computed based on image values, okay? And here the co-occurrence matrix is calculated based on the cluster centers image, so this image. And here is the co-occurrence matrix. Now I plotted the cluster centers on the y and x axis for clarity. Let's read this matrix together. First we see that the diagonal is very dominant because two pixels with the same color co-occur a lot one next to the other in the image. Next we can see that green shades and gray shades tend to co-occur frequently together. Now this is just because gray and green appear a lot in the image anyhow. So they have lots of chances to vote here in this equation. And that doesn't make sense. What we want to do instead is to use the pointwise mutual information, where we normalize those counts by the prior probabilities. So the fact that green or gray appears a lot in the image will not influence as much. So take a look at the co-occurrence matrix, and that's the PMI matrix. It's the same matrix, but now it's normalized by the prior distribution, by the prior probabilities. Sorry. And the PMI matrix reveals an interesting pattern. You see, through the PMI matrix, we're able to see that white and orange has meaningful co-occurrences here in the image. So they co-occur a lot one by the other with respect to their prior probabilities. Okay, so we have everything we need to understand the co-occurrence template matching algorithm, co-occurrence template matching, or for short, co-TM. So we start with a template and with a query image. We first quantize them. Then we collect the co-occurrence statistics. Then we normalize this matrix into a PMI matrix. Now we want to have a score for every patch. Okay? Oh, sorry. A score for every patch. So T is the template, and P is a patch from the query image. And what we do to score this patch is we take corresponding pixels in the template and the patch, and we plug them into the co-occurrence matrix, the matrix M. And we sum those contributions, and that's the score for a single patch. Now we repeat this process for every patch in the query image, and we get this heat map. Finally, we report the patch that maximizes this sum of mutual information. This is the estimation of co-TM. If we want to understand the main difference between SSD and co-occurrence template matching, it's within those two equations. You see, SSD reports the patch that minimizes the sum of square differences. It means that it takes the template and the patch from the query image, it takes corresponding pixels, and it computes the difference, the color differences. Whereas co-occurrence template matching uses the PMI matrix, meaning the probability that those two colors appear one by the other in the image, regardless of their color difference, and it sums them up. So that's the main difference between us and SSD. Okay, here's an interesting property of co-occurrence template matching. So co-occurrences are global features. It's a global feature because we collect statistics from the entire image. Now, why is that important? So I'm showing here the template and a patch from the query image. And here you can see the contribution of those pairs of pixels that I was talking about. And blue encodes here 0 contribution, red encodes high contribution. So you see that the main pixels that contribute are pixels on the tiger. Pixels that are occluded, like those ones, or where we see the background, like here, contribute very little. So it's mainly the tiger that contributes. Now, if we increase the size of the template, it remains the same. So still, the tiger is the main contributor. Even though we added a lot of background to the template, this background does not affect the matching score. Now, this won't happen with local methods. For example, if we would use sift, it would find a candidate here in the intersection between the leaves, and it may match this to any other intersection between leaves, regardless if it's the right template or not. And in fact, the more background we add to the template, the higher the risk of false matches. Now you can see that in co-occurrences, we do not suffer from this. You see, we added a lot of background, but we did not increase the risk of false match. Okay. I would say that our biggest limitation is that we're relying on raw RGB values, which means that if the template and the query image have different illuminations, then we may find false matches. You see, that's the original template, and here I just changed its intensity values. Look at the quantized template. It really changed the cluster centers, which results in false matches. Now, local features like sift, hogs, or more recently deep features use higher level representation, and they're actually immune to such changes. But what limits us from using co-occurrences on those high-level features? So the answer is nothing, and that's what we're actually doing. Here is the input image. Here are the cluster centers based on RGB raw values. Here are the cluster centers of the same image, but now based on deep features. So I'm going to show it again. The input image, RGB-based clusters, and deep features-based clusters. Now, you can see for yourselves that deep features provide a lot more context, and that's why we use that. So we collect co-occurrences on deep features instead of raw RGB values. Here are some example results of our method. So that's the image the template was taken from. The template here is marked by the green rectangle. That's the query image. That's co-occurrence template matching's heat map. And this is SSD's heat map. Now you can see that we managed to find the right template where SSD failed. Here's another heat map by best buddy similarity. It's a local feature-based method. Here's another heat map by DDIS. They are the state-of-the-art as of 2017. And here's another example. The image the template was taken from and the query image, our heat map, SSD. Note that our heat maps are usually very clear, meaning that for most of the image, we say that there is no probability for the template there. Here's best buddy similarity again, and DDIS. Now, naturally, we did not compare ourselves only on 2 images, but on the entire OTB dataset. And you can see here the results of methods that are restricted to use raw RGB values versus deep features. Now, for raw RGB values, co-occurrence template matching was able to score area under curve of 0.62. Notice the large gap between us and SSD. Still, you can see that DDIS outperforms us with raw RGB values only. But now, if we use deep features, you see that SSD closes a lot of the gap, but still co-occurrence template matching on RGB values outperform SSD on deep features. And if we let co-occurrence template matching use the best from both worlds, so both local features like deep features and the globalness of the co-occurrence representation, we're able to score area under curve of 0.67. Okay, there are still some open questions at this stage, like how do we do subpixel accuracies? What about 2D affine transforms? How do you compute derivatives? So for deep methods, gradient descent is very important, so derivatives are important. Let's say for a method like Lucas-Canade, where we approximate the Taylor's expansion, we need derivatives. And the answer to those questions lie within embedding. So what we used is MDS, multidimensional scaling. It's an embedding method that lets us, it's an embedding method that takes the input image and embed it in a space where the L2 distances in the new space match the co-occurrences distances in the original space. So I will explain this now further. Take a look at the input image. In the input image, we see the checkerboard. It's made of black and white. Black and white co-occur frequently in this image. It means that their co-occurrence distance is very small. You see, MDS was able to map them here to similar shades of gray, which means that their L2 distance here is going to be small. Okay, so small co-occurrence distances got mapped to values with small L2 distances. Let's take another example. Let's take the dark and light shades. So dark and light rarely co-occur one next to the other. It means that their distance, their co-occurrence distance is big. And indeed, the dark got mapped to light and the light to dark, but still it preserved the big distance. So when we're using embedding, there's no promise that the values will remain the same. You see, that's dark shades and it got mapped to light shades and light shades to dark shades. The values won't stay the same, but the distances will stay the same, okay? Another thing to note is that once we're using higher dimensionality in the embedding, so in this example, we embed into a 3D space, it makes the results better. So take a look at the input image. Actually, we have 3 regions here. We have the light colors, the checkerboard patterns, and the dark colors. And the light colors were mapped to red, to R. The checkerboards to green, and the dark colors were mapped to blue. So in fact, in 3D, they got mapped to as further as they could, okay? That's the maximum distance we could get between the 3 regions. Let's see some results. So those results are for Lucas-Canade. We apply Lucas-Canade in 2 ways. Here you can see Lucas-Canade on RGB images. And here you can see Lucas-Canade on co-occurrence embedded images. This is the template. The dashed line represents the initial guess in Lucas-Canade, and the solid line represents the result of the algorithm. So you see, on co-occurrence embedded images, the results are much better. The template was mapped to the right location. The same happened for the second row, but now for the second row, thanks to the embedding, we're also able to match 2D affine transforms. You see, that's the 2D affine transform that you get with RGB values, and that's the one you get with co-occurrence embedding values. Now, you see, we managed to find this doll a lot more accurately in the co-occurrence template match, in the co-occurrence embedded image. And of course, we've conducted a thorough analysis on a full benchmark, and you can see in blue the results with RGB values, and in red the results with co-occurrence embedded values, both for Lucas Canade and for kernelized correlation filter. Now, one thing important to note here is that we changed nothing about the algorithm. So when we conducted this experiment, for example, we did no algorithmic tuning. We took Lucas Canade. One time we fed it with RGB values, and the other time we fed it with co-occurrence embedded values. So those gains are in favor of co-occurrence embedded values with no tweaking. Okay, let's conclude the talk. So I presented co-occurrence template matching. It's a method to match pixels by their probabilities to appear one by the other and not by their color differences. I showed that you can compute co-occurrences based on raw RGB values or based on any feature, and we gave the example of deep features. I mentioned that co-occurrences encode global information, which makes them robust to noise, background noise in the template. And I showed that it's easy. So I hope you all use that. That's it. Thank you.
So Roy, can you go back to the picture with the checkerboard and the gray, black, and white?
Sure. Just a second, sorry.
Towards the end, yeah. Oh, never mind, yeah. Okay.
The embedding one?
Yeah, you can do the embedding one.
Sure.
Yeah. So here, you have different embedding for the checkerboard and for the black and white regions because the checkerboard, because it's not black and white, it's gray and...
Right.
But if the black and white in the checkerboard and the black and white on the two sides would have been the same, you wouldn't have this nice separation.
That's right. And you're right that we engineered this example, especially that way, because we wanted to show, just with grayscale values, different textures. So what we were planning to express here is that the checkerboard is one texture, and let's say the gray area with its additive Gaussian noise is another texture.
No, I understand that, but you're comparing it to Lucas and Canade. Now, Lucas and Canade on this thing, if it were, go back. If it were black and white, if the whole thing was black and white, including the checkerboard, including the two halves here, Lucas and Canade would have actually done better than you, wouldn't they?
Yeah. So
because they would have used the gradients and so on.
So for the example where yes. The answer is yes, and the fact that we rely on color, on raw color features makes us less effective in the example that you mentioned, but I imagine that if we would use a higher level feature, then we would be able to...
So what would deep features do in this case?
So
because there's no semantic meaning here.
So I'm not sure deep features would do a good job here, but I guess hogs will do a great job here.
Yeah, okay.
Okay.
Thanks.
Thank you. Thank you.